let's start chapter 3. We spent a lot of time using the limit definition of the derivative to find the derivative of a function at a point or just in general. But it took a long time and it was pretty tricky sometimes. So let's see if we can find some shortcuts to make these problems a little easier and a little shorter. First off, we have to start with what we know. And what we know is that the limit definition of the derivative of a function f of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. This is what we're going to use to prove these shortcut rules. So, number one, what's the derivative of f of x equals 5x cubed? This one's actually not that bad. Let's just do it just to sort of give a refresher, right? Limit as h approaches 0 of f of x plus h is not too bad, right? 5x plus h cubed minus 5x cubed. And when you do this out, turns out when you multiply all that out, you wind up getting x cubed plus 3x squared h plus 3xh squared plus h cubed minus 5x cubed, and then this is all over h. Oh, sorry, I forgot the over h part right here. Okay, you don't need to trust me. You can do it all out. You'll get the same thing. Anyway, when you do this out, you get this, right? I'm just distributing the 5 to everything. Maybe space this out a little bit. Just a little bit. Right, and what we see, sure enough, the non-h terms cancel out, which is good because we're always trying to cancel out that h, right? Now that that's gone, we can rewrite this as, actually maybe I'll just write here in red, times 1 over h, times 1 over h, and we're going to get the limit as h approaches 0 of, and this will be 15x squared, remember the h is going to go away, plus 15xh plus 5h squared, right? Because we divided an h from the top, divided an h from the bottom, and then this gives us an answer, oh no, sorry, I don't even need this limit anymore, of just 15x squared, right? Now, take a look at 5x cubed and 15x squared. See if you sort of notice something, if you notice a relation between those two expressions. Pause the video if you need to, just for a minute. Anyway, that wasn't so bad. You know, it was sort of nice I knew the sort of cubic expansion. What if I asked the derivative of this guy, right? That's a nightmare. I'm not expanding that. So clearly, there's a need for a shortcut, right? So first off, we're going to develop some sort of observations, some facts that'll help us. Then we're going to derive the derivative of a power in general, and then we can finally answer problem 2. Okay? Now, first of all, we use this notation to mean take the derivative of, or the derivative of. So another way to write f prime of x is just d over dx of f of x, right? Okay. So anyway, we're going to show the derivative of f of x plus g of x winds up being f prime of x plus g prime of x. So in other words, you can just take the derivative of f of x, then take the derivative of g of x. You don't have to take the derivative all in one shot. Similarly, if we're taking the derivative of a constant times f of x, take the constant out of the picture and just find the derivative and multiply by the constant in the end. Okay, and now here's the real special sauce. The derivative of x to the n winds up being nx to the n minus 1. Now, this is true for any real number n. Did I include the... Yeah, I'll include it on the next page. It turns out our proof is going to be only for, I guess, non-negative numbers. But with the quotient rule, you can get negative numbers. We'll do that a little bit later on. And when we do logarithmic differentiation in section 3.6, that's when we get all real numbers. So just an FYI. Still, we're going to assume that we know it for all real numbers. All right. So first off, let's prove fact 1. So the derivative of f of x plus g of x, by definition, is the limit as h approaches 0 of, and now it's going to be f plus g of x plus h minus f plus g, right? And that's just the same thing as f of x plus h plus g of x plus h minus f of x plus g of x. Big parentheses, right? Big parentheses, right? All over h. Now, we can regroup this a little bit, right? We can write this as limit as h approaches 0 of f of x plus h minus f of x plus g of x plus h minus g of x, and then all over h. But really what we could do is we could say, well, you know what? I guess we could split this fraction. This can be over h, this can be over h, and we're just adding the two fractions, right? And I guess using, like that's just using arithmetic. I guess using limit laws, assuming that, oh, I don't know why that's interesting. Okay, assuming that both these limits exist, which we'll see that they do. Let's see if I can just shift this over is what I'm trying to do. No, not letting me do it. Well, okay. I'll have to draw another fraction. That's fine. I'm just going to do one of these, right? Because of limit laws, because both of these limits exist, we can actually say that, well, the limit of this plus that equals the limit of this plus the limit of that, assuming they both exist. Well, it turns out they do. Pause the video. See if you can write this and this in a slightly nicer form. Well, it turns out it's f prime of x plus g prime of x, which is exactly what we wanted. So we're done. So the derivative of f plus g is the derivative of f plus the derivative of g. We can use similar trickery for this guy, right? So the derivative of c f of x, right, some constant times f of x, is going to equal the limit as h approaches 0 of a constant times f of x plus h. Note that it doesn't even matter what f of x is. It's just any function, right? All over h. Well, note that we can factor out the c, right? This is the same as just this, right? And note that from limit laws, right, this right here was a limit law identity. This right here is going to be a limit law identity. We can pull the constant all the way out of the limit expression. That was a limit law. And this, by the way, is just c times f prime of x, which is exactly what we were trying to prove. So we're done. So in other words, if you're taking the derivative of some big thing like this, just worry about the x to the 853 and then multiply by 762 at the end. Okay? Now, lastly, let's prove the real meat of this problem, right? fx equals x to the n. Now, I just want to point something out, actually. I'm going to change the color here to orange, just to emphasize the fact that this will not be covered on the exam, nor will anything like it be covered on the exam. You don't need to know this. And same here, actually. This is derivation. I want you to understand it, but you don't need to know it for a quiz. You don't need to know it for an exam. So you don't even need to write this down if you don't want to. Let f of x equals x to the n, okay? F prime of x is going to equal x plus h to the n minus x to the n. All over 8. Oh, sorry. Nope, doesn't equal that. It equals the limit as h approaches 0. All right, limit as h approaches 0 of all this stuff, right? Well, the problem is we don't know what n is. However, we do know a binomial expansion if you're familiar with Pascal's triangle. If not, then look it up. It's really cool. But anyway, assuming we start at 0, the nth row of Pascal's triangle is the coefficients for the nth degree binomial expansion. Or nth degree, expansion of a plus b, or x plus h. Anyway, it's going to give us x to the n plus n, x to the n minus 1, h, plus blah, 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 plus, and then it's going to be, you don't need to write the generic coefficient. You can do it if you want. It involves combinations, just and choose k, right, for whatever k is. And then it's going to wind up being times n x to the h to the n minus 1 plus h to the n, right? All of this minus x to the n, and it's all over h. Now, why is this important? Well, because look what cancels out, the x to the n's. And then at this point, actually I'll keep this in purple, note that every term on the top has an h in it, which is great. That's exactly what we want. So we wind up getting, once we divide out by an h, we get n x to the n minus 1, not times h anymore, right? That goes away, plus, and then everything else has an h in it. And then this is all over 1. Okay? So then this is going to equal nx to the n minus 1, which is exactly what we were looking for. Now, again, this shows it only for non-negative numbers, or I guess positive numbers. You can sort of infer what it is for 0. But we're still going to assume that it's true for all real numbers because it is true. We will prove this in section 3.6, logarithmic differentiation. All right, so again, you don't need to know these derivations, but I do hope you can understand them. All right, so let's do a couple of practice problems. Y equals, now I write the fourth root of x. That's better written as x to the 1/4 plus 6x squared. So dy over dx, the derivative, is going to equal no more limit definition in this case, right? We're going to use the product rule. So we bring the 1/4 down, x to the 1/4 minus 1 plus, okay, 6, bring the 2 down to the 2 minus 1. Oh, did I actually? Yeah, I didn't answer the problem. Okay. So I'll do that later. Okay, and then let's simplify this. This is 1/4 x to the, negative 3/4 plus 12x. Now, I think this is fine. This is mastery, 10 out of 10. But they did give it to you with a radical. So if you wanted to write this in terms of radicals, it would be 1/4 times the fourth root of x cubed plus 12x. Okay. Here, f prime of x, this is going to be 4 times 3.2 x to the 2.2. Right, is everyone see how I got that? Minus 2/5 times 6/7 x to the, that's negative 1/7, right? Because it's 6/7 minus 1. And then what happens to the 5? Right? The plus 5 actually goes away. Right? Because the derivative of 5, I'm just going to write plus 0. Right? It goes away. The derivative of a constant is always 0. It doesn't matter how big the constant is. Anyway, if we simplify this a little bit more, we get this. I guess this is what, 12/35. We did write this as an exponent, so we can keep it as a negative exponent. But if you wanted to, it would be divided by x to the 7th root, or divided by the 7th root of x. All right, g prime of t, well, this is going to equal 99 root 5 t to the 98th plus, what's a better way of writing this? Better way of writing this is 7t to the negative 7t to the negative 1/2. So that's going to be actually minus 7/2 t to the negative 3/2. I did a bit of arithmetic in my head, so if you need a sec, then pause the video. But that's what we get. Now, again, since they gave it to us in radicals, if we wanted to write this in radicals, which we don't need to, but if we wanted to, then we could. It would be 2, and you could either write square root of t cubed, or if you'd prefer, this is how I was taught in high school when I took it, minus 7 over 2t root t. Either is fine. So just take your pick. Now, this is a little messy here, right? We can't just do the power rule straight up. We, need to write it out, right? So it looks like we've got 4x to the 7th plus 2x cubed times itself. And then we just have to multiply it out. We get 16x to the 14th. That's a 14 plus, I guess that's 16x to the 10th plus 4x to the 6th. Now that we've done that, it makes sense to say that dy over dx is going to equal whatever 16 times 14 is. X to the 13 plus, that's going to be 160x to the 9th plus 24x to the 5th. Let's see, 16 times 14, 14, is that going to be 24? 524. I guess that makes sense, 524. So that's going to be 524. Right? Does that? No, that doesn't sound right. No, 124. Hold on a sec. Sorry, let me try that one more time. 5 times 14 is 70. So 15 times that, I think it's 224. Sorry, 224. 224. There we go. 224x to the 13th. Okay. Now, we've talked about polynomials, right? At this point, we can take the derivative of any polynomial, right? Actually, before we do that, let's go back and answer our question. What is the derivative for problem 2? Well, this big, bad, ugly-looking problem is really just going to be, I guess that's 15 and 4, I guess it's going to be 150,000 x to the 299. Right, I won't write it simplified because I don't know how to simplify that other one. It's going to be nasty, but it's just going to be 500 times 300 x to the 299 plus 762 times 853 x to the 852. Right, so it would take a minute to simplify that, but taking the derivative was actually very straightforward. It wasn't really any harder than any of these problems we did, or any of these problems that we did, okay? So the power rule is very, very nice. It works very, very well. All right, now we're going to shift gears from polynomials to exponential functions. Remember that number e? I said it was really important. Well, we defined it to be the limit as x approaches infinity of 1 plus 1 over x to the x. Equivalently, I guess we could, instead of writing x, we could write h, right? Limit as h approaches infinity of 1 plus 1 over h to the h. And I guess it turns out, if you think about it, it's the same thing as talking about the limit as h approaches 0 of 1 plus h to the 1 over h. Just think about that for a second. It works out. So anyway, if you let that equal e, it turns out that you can use that definition to define e in an alternate way. Just using a bunch of simplification and ln's and stuff, which I can do in class if you want to see it, but I won't do it right now. But anyway, it turns out you can define e as follows. Let a be a real number and let f of x equal a to the x. E is the number so that f prime, let me write this, f prime of 0 equals 1. Okay, and again, this is an equivalent way to define a to the x using this definition. Okay, so anyway, why is e so important in calculus? Because the derivative of e to the x is the easiest thing possible. Pause the video and try to guess what it is. The derivative of e to the x is e to the x. You don't do anything to it. So how do we show this? Well, by definition, f prime of x is the limit as h approaches 0 of e to the x plus h minus e to the x all over h. We can factor out that e to the x. Now remember how exponents work. We can pull this out of the whole fraction, and we've got e to the h minus 1 all over h. And remember, with limit laws, we can actually pull the e to the x outside the limit because e to the x does not have an h in it. Well, hold on a second. If you think about it, let me make that a little bit nicer. This is actually the same as e to the x times limit as h approaches 0 of e to the 0 plus h minus e to the 0 all over h, which is the same thing as e to the x times f prime of 0, which we said by definition was 1. So the derivative of e to the x is e to the x. Can't get any nicer than that.